Hello students, Mr. Courtney here, and today we're continuing with atomic structure, and we're looking at mass number versus atomic weight, and we're going to also be looking at calculating abundance. And we're going to start with a review of what we talked about before, and the first thing we're going to talk about is mass number. You remember what mass number is? And if you said it was the number of protons plus the number of neutrons, then you remembered correctly. Now we're going to talk about atomic mass or atomic weight. Okay, so what is atomic mass or what is atomic weight? Atomic weight is the weighted average of the masses of all the isotopes of an element. So we take all the isotopes of the element and we average their mass basically to get the atomic mass. Okay, so that's what it is. It is the weighted average of all the isotopes of an element. And this is the number that we see on the periodic table when we look at an element. So this is seen on the periodic table. And it's usually not a whole number. Most times you see it in decimal form, so it's usually not a whole number. So why is the actual weight of an isotope not a whole number, like the mass number? It has to do with when we talk about E is equal to mc squared. Some of you may have seen this equation before. Einstein's theory of relativity. You may have heard about it. As the object approaches the speed of light, its mass decreases. So here what happens is that the mass, or the mass of protons and neutrons, some of it is converted into energy to hold the protons and neutrons together in the nucleus. So again, some of the mass is taken and converted into energy to hold the protons and the nucleus, protons and neutrons together in the nucleus. Okay, so again, some of the mass of the protons and neutrons are converted into energy to hold okay, what's going on here? To hold the nucleus together. Okay, so how do we calculate atomic mass? Atomic mass is basically the mass of the isotope times its percentage abundance. That is what percent of the isotope is found in nature. What percent of that element is made up of that particular isotope. Now, if there are more than one isotopes of elements, so we have to find the sum of these. So we find what is called the sum. So we take one isotope, then we do the same thing for another isotope. So we find what is called the summation. So that means the sum of mass times percentage abundance. And you do that for all isotopes. So if it has two isotopes, you do this, and then you add it again to the other one. Or if you have three isotopes, you do mass times percentage for each isotope and find the sum of them. That is, you add them together. Okay? Remember what sum means. Together. Add together. Okay? Good. Okay, so now let's look at some examples. In the first example, we're given a mole of chlorine, and we were told that 75% is chlorine 35, 25% is chlorine 37. And if you remember from the first lesson, that the 35 and the 37 actually represents the mass number. And here we have our percentage abundance. So to get our atomic mass, So we have our mass. Let's do the first chlorine, which is chlorine 35 times 75.0 divided by 100 plus the mass of the second isotope, chlorine 37 times 25.0 over 100. Now, before you do any calculation, think about it logically. 75% of the mass is made up of chlorine 35, and 25 is made up of chlorine 37. So that means we should expect our mass to be closer to 35 than to 37. And when we work this out, we get 35.5, and the unit will be AMU. Or there's another way you can do it. It's the same principle, but you need to be careful. We could decimalize the percentage. That is, we take 35 multiplied by 0.750. So we've decimalized our percentage, plus 37 times 0.250. And we'll get the same answer. Now, here's what you need to be careful with. If you're given a percentage as a decimal, let's say you had 0.12%. Most students tend to think, oh, this is a decimal already. I don't need to do anything to it. Yes, you have to do something to it. It's a percent. To convert the percent to a decimal, you must divide by 100. So this will actually be 0.0012 as a decimal and not 0.12. So if you choose to use this method, be sure to convert everything to the decimal by dividing your percentage by 100. If you do this method, do not forget this, please, because you will do the question wrong. Okay. Sorry. Let's get on to the second example. We're given 80% of boron 11, 20% of boron 10. So we do the same thing. Mass times percent. 11 times 80.0 divided by 100 plus 10 times 20.0 divided by 100. And if you work it out to get an answer of 10.8 AMU, atomic mass units. Now, if you need to pause the video at any time and do the calculations because you think I'm going too fast, please do that. So you can pause it, do the calculations, and then make sure that your answer is what I'm getting. Okay? All right. In this example, we've changed it up a bit. We're asking you to still calculate atomic mass, but we've written the elements, the isotopes, in a different form, but we still have all the information. Okay, so we wrote them in a different form, but we still have all the information we need. So the mass of the first element is, or the first isotope, sorry, it's 112. Okay, so we have the mass as 112. Multiplied by our percentage, which is 89.80, and you divide by 100, plus 114 times our percent of 10.20 divided by 100. So again, we always go in mass times percent, mass times percent. Okay. So you work this out, put the numbers into your calculator, you get an answer of 112 it should be. We got 112.204, but since you're only given 4 significant figures, you round that off to 112.2, and that is atomic mass units. And there you have your answer. And again, if you need to take some time, pause the video and do your calculations and then play again. You have that luxury. You're at home. You're not in class. Okay? Let's look at the next one. Now you're given 3 isotopes. So far we've been working with 2. But does that change anything? No, it doesn't change anything. Now, here's an example of what we were talking about before, about the mass number being different. See, it's less. We have our atomic mass for the isotope. We expect it to be 24, but it's actually 23.98504. So which mass would you use in the calculation? Think logically. Remember, think before you ink. So before you start writing on your pen, on your paper, sorry, which one you think we should use? Now, if you chose to use this, then you've made the right choice. This is what we need to use because this is the most accurate mass. Remember, some of the mass is converted into energy. All right. So let's go ahead and solve this problem. We do mass times percentage. This is going to be a long one. Kind of. So we do mass 23.98504 times our percentage 78.99 divided by 100. Okay, that's for our first isotope. Our second isotope, magnesium 25, 24.98584 multiplied by 10.00 over 100. Now I'm going to put these in parentheses, so that's going to make it a bit easier for me because I have to go on to the second line. So that's plus magnesium 26, so that's 25.9898, 25.98259 multiplied by 11.01 over 100. So take your time, work these out. Now you should be able to put this into your calculator, everything at once, and work it out. Now some of you may want to go do this part, find the answer, write it down. Then do this part, find the answer, write it down. Do this part, find the answer, write it down. That's just too many steps. Plus, you're more likely to have a mistake, to make a mistake when you do this. Either you transpose the numbers wrong when you put it into the calculator, or you write the numbers down wrong when you take it in from the calculator. Somewhere along the line, you're going to make a mistake. The best thing to do is put this in directly. Put these in parentheses, do this. Then add this, and that gives you your answer immediately. And that's going to give us an answer of 24.31 AMU. Okay? So if you need to go over this again, pause the video or go back, rewind, and play the video again and get it done. Okay? Okay, and the last one, and I'll read the question. The atomic weight of gallium is 69.72 AMU. The masses of 2 naturally occurring isotopes are 68.9257 AMU for gallium 69 and 70.9249 AMU for gallium 71. Calculate the percent abundance for each isotope. So here's what we're doing now. We're given the atomic weight to start with. Okay, so we're given atomic weight, which is here. We're given the masses of the isotopes, and we're given the isotopes. And we're told, go ahead, have that information, now calculate percent abundance. So we're going back. We're going to have to do the process in reverse. So how are we going to solve that? First thing you need to do, think about it logically. You know how to calculate atomic weight. So let's start by writing the equation to calculate atomic weight. Okay, so let's write the equation to calculate atomic weight. So our atomic weight of 69.72, we know that is equal to mass, which is, let's use our first isotope, 68.9257 multiplied by the percentage abundance of gallium 69 plus the mass of our second isotope, 70.9249 times the percent abundance of gallium 71. So how are we going to go about solving that? Now look, we have determined how many unknowns we have. 1, 2, but we're given one equation. And if you remember from algebra, if you have two unknowns, you need two equations. So let's come up with another equation. Since we're dealing with percentages here, we know that 100% or 100 would be equal to the percent of gallium 69 plus the percentage of gallium 71. So we know that they're going to be add up to 100. Or if you want to divide by 100 and decimalize it, that becomes equal to 1. And it would be easier to work with 1 in this case. So let's do that. And I say now let y equal the percentage abundance of gallium 69. So that means y, if I put it into this equation here now, y would be equal, not equal, sorry, y plus gallium 71, and that is the percentage of gallium 71 will be equal to 1. So therefore that means the percentage of gallium 71 would be equal to 1 minus y. So we have made our unknowns in terms of y. Okay, so we have y. So here are the two unknowns that we're going to use. So we have y is equal to the percentage abundance of gallium 69. Or we have, and we also have y, 1 minus y is equal to the percentage abundance of gallium 79. So we're going to take this and substitute it into our original equation. So that gives us now 69.72, and there's a point here, is equal to 68.9257 y, because that's gallium 69. So we substitute the percent of gallium 69 with y, plus 70.9249 multiplied by 1 minus y, because that is the percentage abundance of gallium 71. So we go ahead and expand this. 69.72 is equal to 68.9257 y plus 70. Okay, so we do 70 times 1. Okay, so 70 times 1 gives us 70.9249 minus, now this times y, and since it's negative y, that's how we get the minus sign. It's minus 70.9249y. Now you remember in algebra? Yes, so remember algebra now. Yes, I know it's chemistry. I know it's chemistry, okay? So take a deep breath. Don't let the numbers get to you. Think about the process. Think about the process. We need to solve for the unknown y. So how about we group our like terms together? So 69.72 minus 70.9249, that would be equal to 68.9257y minus 70.9249 249y. So if we go ahead and solve this now, so we subtract everything on the left side, this leaves us with negative 1.2049. That is equal to negative 1.9992y. So that tells us that y would now be equal to negative 1.2049 divided by negative 1.9992. So y is equal to 0.60269. So that's what y is equal to. But remember, we had divided by 100. So the percent now of gallium 69, since y is equal to gallium 69, so we take y and multiply by 100, 60.27%. Okay, so again, this here multiplied by 100 gives us this if we round it off to 4 significant figures. So our percent now of gallium 71 would be equal to 100 minus 60.27. That gives us 39.73%. So there you have it. Yes, I know it seems like a lot of work, but if you think about it logically, just follow the process. All right, you may need to play it over again, or just look at it over, think about algebra, and you can get it. Okay, so that takes care of it. Remember, we just looked at how we calculate atomic weight, and if you want to do, just look back quickly. Remember, atomic weight is calculated based on mass times percent abundance, and atomic weight is the weighted average of all the isotopes of an element. Okay, all right, hope this was helpful to you guys. Until the next time, blessings. I'm out.